Now, welcome you back in this. This is your our ninth lecture on metric spaces, and today we will discuss the closure of a set and the relation between the closure of a set and the closed set. Okay, so we have already defined the limit point, and then we will define the closed set. Okay, so the closure of a suppose X is a metric, X is a subset of a metric space X. The closure of A is denoted by over line A, okay, or CLA. The closure of A is denoted by either this way or by this way, and the closure of A is the union of A and the set of all limit points of A. That is, the closure of A is equal to A union derived set. Okay, in other words, you can say that an element X is in the closure of A if every open sphere, because every open sphere SRX with center at X and radius R contains a point of A. Okay, in other words, you can say that X is an element of closure of A if and only if SRX intersection A is non-empty for every R is greater than 0. So, closure of A is the set of all points of A, and you can include the limit points of A. For example, we have considered the set A is equal to 1 over 2, 1 over 1, 1 over 2, 1 over 3, 1 over 4 and so on. So, no point of this set is the limit point of A, but 0 is the limit point of A. So, you include 0 here, and that would be the closure of A. So, if you have the set A is equal to, for example, if you have a set A is equal to your 1, 1 over 2, 1 over 3 and so on. Okay, of course, it is a subset of R and is with the usual metric. Then the 0 is the limit point. 0 is the limit point of A. So, the closure of A is equal to A union the derived set. It means that it is 0, 1 over 1, 1, 1 over 2, 1 over 3 and so on. So, this is the derived, this is the closure of A. Okay. So, this way we can define the closure of a set. Okay. Now, the closure of empty set, it is customary that the closure of the empty set is the empty set. The closure of the whole space is the whole space. Similarly, the interior of empty set is empty set, interior of whole space is whole space. And we will see that the interior, the empty set and the whole space are both open as well as closed. We will see the definition later. And the set A is always a subset of closure of A, because the closure of A is the union of this one. So, of course, the A is a subset of closure of A. So, this we can write this. The closure of A is equal to closure of A, and closure of A is equal to the derived set of closure of A, because it also always contains the limit point. So, it is same. And if A is a subset of B, then we can say that closure of A is a subset of closure of B. You can prove these things, these properties by as we have proved for the interior. And the closure of A union B is equal to closure of A union closure of B. Okay. And if we take the intersection, then closure of A intersection B is a subset of closure of A intersection closure of B. but the reverse inclusion does not hold. That is to say, the closure of A intersection B may not contain a closure of A intersection closure of B. For example, we can consider, as usual I am considering all the time, so most of the time, not all the time, most of the time, the usual metric space R. So, and you can take the set A is equal to open interval 0, 1 and B is the open interval 1, 2. Then the closure of A is equal to the closed interval 0, 1. Closure of B is the closed interval 1, 2. Okay. And then the intersection of closure of A intersection closure of B is equal to closed interval 0, 1 intersection closure, and so it is equal to 1. But if you take the A intersection B, so A intersection B is equal to what? It is equal to empty. Okay. And the closure of empty set is empty, so this is equal to empty set. But here is, you see that this is 1 and here is this is empty, and therefore closure of A intersection closure of B may not be a subset of the closure of A intersection B. Now we have a very important property, and that we will use throughout this in several results, that if XD be a metric space and A be a subset of X, okay, then X lies in the closure of A if and only if the distance from X to A is equal to 0. Okay. If the distance from X to A is equal to 0, the distance of X is equal to what? It is equal to the infimum, the distance from X to A is equal to the infimum dxy, and y is in A. So infimum we are taking over A. Okay. So if the distance from X to A is equal to 0, then X lies in the closure of A, and if X lies in the closure of A, then this distance is equal to 0. Keep in mind, I am not considering here A, it is the closure of A. This is very important and I will show you later. Okay. So let us prove this. So suppose X is in the closure of A, then we will prove that this is holds good. Okay. If X is good, if then because of the definition closure of A is equal to A union B, then X can be an element of A or closure or drive set. So suppose X is in A, if X is in A, then dxx, because infimum of A, so here we are taking the infimum, or X is in A, so this would be equal to 0. Okay, so we will get the answer, no problem. So assume that X is not in A. So X is not in A, then X must be a limit point of A. Okay, so X is a limit, it means that for every epsilon positive, there exists a point Y. Okay, for every epsilon positive, the open ball with center at X radius R intersection A, this must be non-empty. So this is non-empty, so there must exist a point Y in this set. It means what? It means that the distance between X and Y is less than epsilon. Okay, so distance is less than epsilon. Now by the definition, rho XA is equal to the infimum of dXA such that X is in A. Now we are taking the infimum. So you take epsilon is very, very small. So if you take the infimum of this, okay, then you will get this is equal to 0. Say for example, epsilon is equal to 1 over n as n tends to infinity. So this will tends to 0, and therefore because we are taking the infimum, so it will be equal to 0, and therefore this is equal to 0. So this is very important. Now here is as I mentioned that here is the important thing is we are considering X is in the closure of A, okay, not in A. So let's prove the, okay, so here is we can prove, and now we prove the other way. Other way means that if this is true, then X lies in the closure of A. So suppose that the distance from the point x to a is equal to 0. Okay. If we have to prove that x is in the closure of A. If x is in A, then x is in the closure of A by the definition of the closure of A. So nothing to prove. So suppose that x is not in A. Okay. X is not in A, then by the property of the infimum, for every epsilon positive, there exists y in A such that dxy is less than epsilon. Okay. Because we are considering because of this. Okay, because this dxy, this is less than epsilon. It means what? It means that y lies in the open sphere with center at x and radius epsilon, and of course it is in A, so intersection A. Okay, and now since x is not in A, so y must be in this one. Okay, and this then x is not in A. X is not in A, so y cannot be equal to x, so y cannot be equal to x. Okay, so y, it means that y is an element of this set other than x. It means what? It means that y is a limit point of A. So it means that x lies in the derived set. It means that x lies in the closure of A. So this is the way to prove this result. Now, here is basically, instead of writing this, we will see that here is this must be the closure of A. Okay, we can replace later we can replace this closure of A by a closed set, but we cannot say that x is in A if and only if rho x A is equal to 0. This we cannot say. Now, before coming to the other results, let us define the closed set. So, a subset A of a metric space X is said to be closed. Okay, is said to be closed if it contains all its limit points. Okay, that is to say, the closure of A is a subset of A. But closure of A is a subset of A. But it means that it is obvious that A is closed if and only if closure of A is A. Okay, because if it contains all its limit point, so all its limit point means that derived set must be a subset of A. And the closure of A is what? Closure of A is equal to A union derived set, but derived set is already contained in A, and therefore the closure of A is equal to A. So, a set is closed if and only if closure of A is equal to A. As we have already proved that the set A is open if and only if the interior of A is equal to A. The same as here, a set is closed if and only if the closure of A is equal to A. Now, we have some examples of the closed set. Suppose we are considering the real line with the usual metric, then the set of all rational numbers and the set of all irrational numbers are not closed. Why they are not closed? Because the closure of A is equal to A, we have proved. Okay, if we are considering set of all rational numbers. Okay, so set of all rational numbers, and what is the derived set of the set of all rational numbers? Is the whole real line. Okay, but the whole real line, okay, the derived set, whole real line, and whole real line is not the subset of set of rational numbers, and therefore it is not closed. And similarly, the set of all irrational numbers are not closed. Now, suppose we consider the set A consisting 1, 1 over 2, 1 over 3 and so on. Okay, then we have seen that the limit point of this set is 0. That is to say, the derived set of this set consisting only element 0. Okay, but 0 is not in A. So, the A is not closed because that the derived set must be a subset of A, then the set is closed. So here is the the derived set is not a subset of A, so this set is not closed. Now we are considering A is equal to this set. Okay, if A is equal to this set, intersection n runs from 1 to infinity, close interval minus 3 to 1 upon n, open interval. Then we will see that the closure of A, so as we have seen that the limit point of this is what? The limit point, the closure of this set is equal to minus 3, 0. Okay, so minus 3, 0, this set is equal to the A. No, it is not equal to the closure of A is equal to A. So this is equal to A. In general, it is so the closure of A is equal to this one. Okay, similarly, we can say that if A is the set of all irrational numbers, rational numbers between the open interval 0, 1, then the closure of A is the whole, all the elements, that is the closure of A is the closed interval 0, 1. The Cantor set C is closed as the derived set is equal to A, and which A is a subset of A. Now here we have a remark. We say that every finite set, empty set, whole set are closed sets. So every finite set, empty set, whole sets are closed. Okay. Now we can see that very easy that in a metric space, the A is closed, a set A in a metric space X is closed if and only if the complement of A is open. So this is very simple, very important. The complement of a set is closed if and only if the complement, if its complement is open. Or you can say that a set is open if and only if its complement is closed. So to prove this to prove this result, let us assume that A is closed. Okay, and then we will prove that the complement of A is open. So we have to prove that we have to consider X in the complement of A an arbitrary and prove that it is the center of some open sphere contained in it. So X is in A, then X cannot, the X is in the complement of A, then X cannot be in this set. Okay. So you can see that suppose I take here is the small one, this is my set X. Suppose this is the set A and this is the portion of complement of A. And suppose X is here, okay, then X cannot be in A, okay, and also X cannot be a limit point of A, okay, X cannot be a limit point of A because A is closed. So A is closed, so A contains all its limit point. So it is outside, so it cannot be a limit point of A because A is closed. Okay, so this is not in A. Okay, and it is also not a limit point of A, and therefore you can see that you can always find an open sphere such that SRX intersection A is equal to empty. This you can find. It means that what? It means that this open ball lies in the complement of A. So this means that this open ball lies in the complement of A for some R. It means what? It means that this is X is the center of some open sphere contained in this one, and since X was arbitrary, It means that each point of complement of A is the center of some open sphere which is contained in the complement of A. Therefore, the complement of A is open. Okay. Now, let's prove this. The converse. To prove the converse, we can assume that the complement of A is open. Okay, the complement of A is open, then we will have to prove that A is closed. So let X be a limit point of A. X be a limit point of A. So we will have to prove that the every limit point of A lies in A. Then A is closed. Okay, so X is the limit point of A. Okay, so if X lies in A, then A contains all its limit point and hence A is closed. So nothing is proved. So we assume that X is not in A. X is not in A, then X must be in the complement of A. And complement of A is open. Okay, because we are assuming that complement of A is open. So X must be must be a center of some open sphere contained in this one. So there exists an open sphere SRX contained in the complement of A. It means that the intersection of the open sphere SRX and A must be empty for some R is greater than 0. And hence X cannot be a limit point of A, which contradicts to our supposition that X is a limit point of A, and hence X must be in A. So this which we are assuming, it is not true. So X must be in A, and this proves that A is closed. Okay. Now we will prove that in a metric space XD, every closed sphere is a closed set. Okay, as we have proved that every open sphere is an open set. Similarly, every closed sphere is a closed set, and this we will prove in the next talk. Thank you very much.